we first need to understand what happens when we multiply a vector by a matrix. So let's suppose we have this vector, right, in some xy plane, and let's say this is uh, let's say this is 3 by 4. Um, this point is 3 by 4, and this is a 3 matrix. Let's call V as 3, 4 vector. Okay, and let's suppose I have a matrix A that is 1, 2, minus 2, minus 1, right? This is just a random matrix, and I want to multiply um, A by V, right? So what happens if I multiply this? So let's see, let's work out. So 3, so this is 1, 2, minus 1 multiplied by 3 and 4, and this gives us a new vector 11 and minus 10. So this is a new vector, right? Let's call it V V2. Let's suppose this was V1, and this new product is V2. So let's plot this V2. So this is 3, and then 11 would be somewhere over here, and is 4 and minus 10. I'll have to extend it. So it will be somewhere over here, right? This matrix is 11 minus 10, right? So what you're seeing is that when you multiply a vector by a matrix, it rotates this matrix by some angle and also stretches it, right? So there are two things happening at the same time. When you multiply a vector by a matrix, the vector gets stretched and it's also get rotated. However, there are certain uh, vectors, when you multiply them with your original A matrix, they don't get rotated, they only get stretched in the same direction. So they maintain their direction. So such vectors which only get stretched, for example, if V1, let's say V3 is such vector, it doesn't change its direction. Only the scale gets changed, right? It becomes lambda times V3. So the vector remains the same, only the magnitude changes. So if this is a situation, then we say that V3 is actually an eigenvector of this matrix A, right? So this is the concept of eigen vectors, and this value is called as the eigenvalue. The lambda over here is the eigenvalue, right? And this is the eigenvector. So we have to understand this concept of eigenvectors and eigenvalues in order to understand how this works. And we must also notice here that this thing works only if A is a square matrix, right? And its dimension should be n by n if we have an n vector over here, right? If there are n dimensions in this vector, then we must have an n by n matrix, because otherwise this won't work. Let's suppose A were rectangular, and we have something like A is equal to 1, 2, minus 2, minus 1, 1, 1, and we try to multiply it by the same vector. This will give us an error because the dimensions don't match. Similarly, if we have A something like 1, 2, 1, minus 2, minus 1, 3, and we try to multiply it again by 3 by 4, you will see that we'll get an error again, right? So in that case, this for this eigen thing to work, it must be a square matrix. But what if we start off with a matrix that is not a square matrix, and it's a rectangular matrix, and we want to find out the eigenvectors and the eigenvalues for that vector. Let's suppose this is our A vector, sorry, A matrix over here. 1, 2, 1, minus 2, minus 1, 3, and we find out the eigenvectors. So what we can do is, as a matter of fact, is that we can employ a trick. We can multiply this matrix by its transpose, and this will give us a square matrix. Which is in fact equal to the A matrix minus 2, minus 1, 3 multiplied by its transpose 1 minus 2, 2 minus 1, 1 minus 1 and 3. And when we multiply these together, we get a square matrix. We get a square matrix 6 minus 1 and minus 1 and 40. So you do the computation. Now this is a square matrix, and we can find eigenvectors for this one, right? And similar for eigenvalues. But since it's a product of two matrices, right? These values are actually the square of the eigenvalues for individual matrices. So what we get is we get singular values for this product, and the singular value for this matrix is actually the square of the eigenvalue for the, so if I calculate the eigenvalues for A over here, right? If I just calculate eigenvalues, I'll get two eigenvalues. One is 5.87 and the other one is 14.12. Where did I get this from? I'm just obtaining this from MATLAB directly, because right now I'm not taking you through the steps that are required to calculate this value, but essentially it means solving this equation, right? Making use of the fact that A is invertible and therefore its determinant should be 0. So we make use of that, and then we solve this and we get the value for lambda. For the value of lambda, there will be two values, because if you look at this, we have two set of equations, one over here and the second one over here, right? So when we solve two linear equations simultaneously, we get two values, two solutions or two roots, and these roots are these lambdas over here. And if I do it directly on MATLAB, I get this. And similarly, if I take this matrix over here, the square matrix that I have obtained from this, A multiplied by A transpose, and I get this vector. And when I use MATLAB to find out its eigenvalues, which I have obtained by multiplying A by its transpose, I get two eigenvalues, right? So I get sigma 1 as 3.75 and sigma 2 as 2.42. Now, if you look at this value over here, and you look at this value over here, you'll see that this value is actually the square of this value. So when you square sigma 1, you get this value. Similarly, when you square sigma 2, you get this value, 5.87. So there is a link between the singular values of A and the eigenvalues of A. Obviously, we cannot like have singular values of We cannot have eigenvalues of A if A is rectangular, right? But if A is rectangular, we make it square by multiplying it by its transpose, and then we find its eigenvalues. Those eigenvalues are called as its singular values, right? So singular values are square. When you square singular values, you get eigenvalues. We can do another thing over here. So instead of multiplying A by its transpose, we can also multiply A transpose by A, and we'll get another square matrix, but this time a different one, because we have changed the order of multiplication. So when we do that, we multiply A transpose by A, we again get a square matrix, but this time the dimensions are different, right? Over here it was 2 by 2, but this will be a 3 by 3 matrix, because A transpose is the long one, right? This is the long matrix over here, and we are multiplying it by the short matrix over here. So the result will be a matrix that is bigger in dimension, right? So if we take, for example, this A over here and do A transpose A, we'll get a 3 by 3 matrix over here, which is 5, 4, minus 5, 4, 5, minus 1, minus 5, minus 1, and 10. So I use MATLAB to calculate this, right? So you can verify. So, but this is a 3 by 3 matrix over here, right? So let's look at eigenvalues of this square matrix over here. So if I calculate the eigenvalues of this new product, A transpose A, interestingly, we get the same eigenvalues. We get 5.87 and 14.12, and we also get a third one, but that is close to 0, right? So we can simply ignore that one. So so this way we can find not just the singular values for this product, we can also find singular vectors for this square matrix over here, or singular vectors for this square matrix here. The singular vectors for this square matrix will be called as U, and singular vectors for this square matrix will be called as V. These eigenvectors are normal, which means they are of unit length. They're they are unitary vectors, and so are V. They're also unitary vectors, right? They have length 1, and they also have length 1. The not this matrix, but the eigenvectors of this matrix, and not this matrix, but the eigenvectors. Sometimes we call them as left eigenvectors and right eigenvectors, and sometimes we call them as left singular vectors and right singular vectors. Matrix is not U, right? U is the set of eigenvectors for this square matrix, right? Similarly, this is not V. V is the set of eigenvectors for this square matrix over here. So don't get confused. That's why I've drawn a line over here, right? So this thing is not U, and this thing is not V. U is a matrix that we can calculate, and V is also a matrix that we can calculate based on the singular values that we calculate from these two vectors. And these singular values remain the same. So we just have one sigma, right? It's a diagonal matrix, and it will in this case we'll have 3 values over here, right? The first one will be 14.12, the second one will be 5.87, and the third one will be 0, and then we'll have zeros everywhere else in this diagram. So this is the sigma matrix over here. So if we have A, this was our A, right? Rectangular A. We're not talking about this one. I should have used another letter for this matrix. But anyway, let's call this as A1. So to remove the confusion, this is also A1 over here. So the rest of it is A, which is a rectangular matrix, right? And we have done all these calculations to find out U, V, and sigma. So if this is A, this can be decomposed as U, sigma, V transpose over here, right? And in the next step, we'll see how to actually compute these. Okay, so let's do an example where we actually um, take a matrix and decompose it into these three components. So let's start with an example. All right. So what is the first step? The first step is to multiply A by its transpose. So we have 3, 1, 1, minus 1, 3, 1, multiplied by 3 minus 1, 1, and 3, 1, and 1. And when we do the multiplication, we get a square matrix. 11, 1, 1, and 11. Now you can see that this is a 2 by 2 matrix, although in the original matrix there were just 2 rows, and when we multiply it by its transpose, which has 2 columns, we get a 2 by 2 matrix, right? 2 by 2 matrix. Now let's find out the eigenvalues for this one, right? So we know that eigenvalues are those values that just stretch any vector that gets multiplied by this matrix, right? Suppose that this vector is x1 and x2. This will be, let's call it lambda vector, and this will give us back the original matrix, which is stretched by this lambda over here. So we can expand this we can rewrite this as a set of 2 equations. We can write it as 11x1 plus x2 is equal to lambda times x1, and then the bottom one becomes x1 plus 11 times x2 is equal to lambda times x2. So these are 2 linear equations. We solve them simultaneously, and we get 2 values for lambda, which is lambda 1 is equal to 10 and lambda 2 is equal to 12. Right? We plug these back in this equation one by one to find out the values for x1 and x2. That will be our eigenvector for this matrix over here. So x1 and x2 is equal to, for these 2 lambdas, we get 2 equations. One is x1 is equal to x2, and for the other lambda, we get x1 is equal to minus x2. You can verify this by doing your own calculations. Now we'll have to use this information in order to actually find out the unit vector that will be the eigenvector for this matrix over here. So let's do it. Okay, this means that we have 2 eigenvectors. We have one eigenvector as 1, 1, and in this case the eigenvector is 1 minus 1. Right? And we can express both of them as a matrix. Right? This is the first eigenvector, and this is the second eigenvector. Right? So this is actually we're coming close to U, right? The only reason this is not U is that these are not normalized yet. So we have to divide them by their magnitudes to get U. Okay, so we have a matrix. Um, let's call it as U prime. Okay, I'm calling it as U prime because these vectors are not normalized as yet. Although they are eigenvectors for this matrix over here, they are not normalized. It means they don't have unit length right now. For example, the first one, the magnitude is under root 2, right? So we need to find out a way in which we can express them as a set of two normal vectors, right? So for this, we use a procedure which is called as Gram-Schmidt procedure for taking a set of vectors and converting them into a set of normal vectors, right? So I'll explain that procedure in a bit, but right now I'm just using that procedure. So I'm using that Gram-Schmidt procedure in order to convert them into orthonormal vectors, and what I get is my U. I'll just write it out right now. This is 1 over under root 2, and this is also 1 over under root 2. And you can see that this is just simply, I'm just making it normal by dividing the first vector by its magnitude, right? And use this one to calculate the other normal vector, which in this case turns out to be very similar. 1 over under root 2 and minus 1 over under root 2. But if there were some other values, we might have ended up with a different set of values over here. But the concept is that you first normalize the first vector by dividing it by its magnitude, and then use that in order to calculate, you use that to express the second vector in terms of the first vector, right? So you kind of project this vector onto this vector, and therefore that's how you apply the Gram-Schmidt procedure. So I explained those steps in a bit, but if we follow those steps, we end up with this U. Let me write it more clearly over here. This is 1 over under root 2, 1 over under root 2. This is 1 over under root 2 again, and minus 1 over under root 2. So this is a 2 by 2 matrix, and this is my U. So I have identified U with the help of lambdas that I calculated by first taking the transpose over here, right? In order to find V, I start off with A transpose A, and then follow all these three steps again, right? So I'll end up with V. I'll find out what V is. So V will be a 3 by 3 matrix, right? So this is 1 over under root 6, 2 over under root 6, and 1 over under root 6 again, and 2 over under root 5, minus 1 over under root 5, and 0, and 1 over under root 30, 2 over under root 30, and minus 5 over under root 30. And this is my 3 by 3 V matrix. And I have to get its transpose to fit in this formula. So I have A, which I've decomposed into U, and a sigma diagonal matrix, and a V transpose matrix. So U is over here, V is over here. I take its transpose and put it over here. And what are sigmas? These are just these lambda values over here, right? but obviously they are scarce. So I'll for for singular values I'll take the um, under root of these two values. So my sigma is actually under root 12 and under root 10, and I have got zeros in other places. So it's a 2 by 2 matrix with singular values that are square roots of the lambdas calculated over here. And I've shown you how to calculate U and T. So the last step that remains is how to perform this Gram-Schmidt normalization, which will be my next step. Okay, so over here I'll show you the Gram-Schmidt procedure of taking a matrix which is not normalized and converting that into a normalized matrix. Okay, so what is the first step? The first step is to take the first vector, and I just divided it by its magnitude, and I get a column vector which is now normalized, right? Because if I take this vector and find its magnitude, it will be 1. Okay, so I have normalized the first vector. Now I have to normalize the second vector. Okay, and I do that with the help of a formula. Okay, so in order to follow the Gram-Schmidt procedures, I'll go graphical from here, right? So I've just taken two vectors. This is one vector and this is another vector. And I have to do two things now. I have to express both of these vectors. Let's call this as A, and this is the B vector, and this is the A vector. So I have to represent both A and B in terms of unit vectors that are orthogonal to each other, right? So I'm looking for two vectors that are perpendicular to each other, but they express the kind of the same. I can express both of them in as using the same units, right? So if I, for example, in Gram-Schmidt, what happens is that I take the first vector A and divide it by its length. So I get another vector which is of unit length. Let me call it that A hat, right? Now A hat is a vector that is of unit length, right? So it's normalized. Now I have to find another vector which I can add to this vector A over here, so that I can get to this point, the endpoint of B. Okay? So I'm looking for a vector which is perpendicular to A, right? And I'll have to multiply it by some factor so that I get to this point, and I also have to multiply A by some factor to get to the place where I can add this vector. So what actually happens is that I'll continue in this direction, and at one point I'll then go perpendicular to it, right? And let's let's call this as a W vector. Now, so I have this vector over here, from over here. It can be expressed in terms of this unit vector over here. So it is some scalar multiplied by A, and I have to add W to this. This is W over here, right? So this thing plus W will be equal to my original vector B, which I want to express in terms of two orthogonal vectors. So, but this W is not of normal length, right? So what I have to need is I have to find a unit vector in this direction, direction of W, so that I can express both the original A and B in terms of two unit vectors that are orthonormal. So there's some combination of A in this direction plus some combination of B in this direction. Right? A hat in this direction and B hat in this direction to get to this point over here. So I'll use this, and I can rewrite as W is equal to B minus SA hat. So I have to find out this scalar over here and this B over here, right? This B is the original vector, this one was over here. So we already know this thing. We have to find out this S over here. So it is simply, if you look at this diagram, it is simply the inner product of the original vectors A and B. And that gives us the scale, right? So I just can write it as A dot B, right? And then I multiply this by this unit vector over here, A hat over here, and this is B over here. So this is my new W over here. This remember, this is in this direction orthogonal, and finally I have to normalize this by dividing it by its own magnitude. So let me do these calculations over here. So in this case, if I call this as V1 and this as V2, then this one is actually U1. This is my unit vector that is normalized in this direction of V1, right? This is this one over here, right over here. So the orthogonal vector, let me call it W2, will be equal to V2, this over here, V2, minus this S over here, which is simply the inner product of this U1 over here with the original V2. So I'll write U1 dot V2. This is the inner product or this scalar product. And then I multiply this whole thing in this direction, right? This is U1. And let me plug in the values over here. So V2 is 1 minus 1 minus U1 is this one over here, 1 over under root 2, comma, 1 over under root 2, dot, this is the inner product of with V2, which is over here, 1 minus 1. And then I multiply it by with this U1 over here, which is this one, 1 over under root 2, comma, 1 over under root 2. And when I simplify all this, I get W2 is equal to 1 minus 1 minus 0, 0 is equal to 1 minus 1. To normalize it, I divided it by its magnitude. So I get U2 is equal to 1 over under root 2 and minus 1 over under root 2, and which I can write over here, 1 over under root 2 and minus 1 over under root 2. And this is my U2. So these both of them have unit magnitudes now, and they're also perpendicular to each other. And we have found this out through a procedure called Graham-Smith, and this was a rough idea of how Graham-Smith procedure works. Basically, you normalize the first vector, and then you find an orthogonal vector that, when added to the first one, gives you the second vector. So now I can use this back in my calculation to show where did I use these. was before. This is the U, big U that I calculated, right? Using Gram-Schmidt. Over here, I just mentioned the name, didn't tell you the procedure, but now you know the procedure. And so this is U1. Let me just write it as U1 over here, and this is U2 over, and this is a big matrix U over here. The big matrix is orthonormal, which means all its vectors are of unit length and they are perpendicular to each other. And the same goes for V over here. This is a 3 by 3 matrix, but I also calculated using exactly the same procedure, Gram-Schmidt and everything. Right? So once you have calculated the lambdas, you can calculate the sigmas, and you can calculate the U and V, and that's how you can transpose the original matrix A over here into its three components, U, sigma, and V. Right? If you multiply them all together, you will get back this original matrix. So what's so good about this decomposition? The good thing about this decomposition is that it find out what are the directions in which there is maximum variation in this matrix. So in other words, where is the information hidden in this matrix? So right now, since they are correlated, these vectors, they're not orthogonal to each other, these matrices. It means they're not linearly independent. It means that this vector can somehow be represented as a linear combination of other two or at least one of them, right? But when we decompose it, they are all orthogonal to each other. It means you cannot express one in terms of the other as a linear combination. It's not possible. They are distinct in distinct directions. So which direction is more important? Which direction gives you more of the variation so that you reconstruct this original one that is given by this scaling factor over here, right? So this is how you extract information from a rectangular matrix using SVD. If there are any questions, please send them via email to me.